Good evening. This is Dennis Cruz, and this is the weekly report of the SciPass internship of the week starting in June 22 of 2020. All right. For this week, the paper I reviewed is on the state of art and future directions for lower limb robotic exoskeletons, which is share my screen here. All right, let's start from the beginning. The author of the paper is Aaron J. Young and Daniel P. Ferris, and it was published in the Transactions of Neural Systems and Rehabilitation Engineering from the IEEE. All right, let's get a little bit of a background here. Move this around. Of the current state of the art, there are some limitations in the design and the performance details for exoskeletons. It is very difficult to assess the current state. One is because of the speed of technology development, and the other one is the availability of scientific publications in the field. The lack of peer-reviewed journal articles that describe the test devices is what I mentioned, that there's not a lot of scientific publications about exoskeletons right now, and the speed of technology development, because sometimes there's some technology that it could be required to design and develop exoskeletons, but it's just not available yet because there haven't been much research about it. All right. The other one is the other states about the human performance augmentation metrics, which is what's the standard for human. What's the moment of the human? Like, how do you measure how good it works exoskeletons with humans? The most common metric is measuring the metabolic costs of locomotion under walking or running conditions with and without the exoskeletons. For devices that are focused on solely assisting able-bodied individuals with locomotion, metabolic cost is clearly the most accepted metrics. Very few studies have shown a statistically significant decrease in metabolic cost during locomotion when using the exoskeleton. And the other metric is it is difficult to evaluate robotic exoskeletons that provide assistance for lifting objects and performing work, because there is not like you need a lot of sensors to determine how much work a human is using, or it's hard to evaluate that. Another measure that is not mentioned here is the energetics, which is how much energy you use to perform a certain task. That's what's difficult to measure. And fatigue, productivity, and safety are also relevant and important factors for the exoskeletons. And the current state of the devices. Here are some of the devices that are right now or that have been developed or it's been under study. The first one is called Bleaks. Well, like as I mentioned, there's a number of different research groups and technologies, but the two exoskeletons prototypes were the most visible, which is Bleaks. It stands for the Berkeley Lower Extremity Exoskeletons, whose goal was to develop a portable robotic exoskeleton that allows soldiers to carry heavy loads over long distances. The next one is the Sarcos, which is a company founded by Stephen Jacobson. The Sarcos exoskeleton evolved into XOS after Sarcos was acquired by Raytheon. Well, the exoskeletons were a full body suit that supported the body, arms, and legs with the intent of amplifying the user's strength. The exoskeleton powered is by joint rotary hydraulic actuators connected to a tether power source. Due to high electrical energy demands of the prototype, it was not made fully portable, so it has to stay connected to a power source. All right, the next one is called Fortis, which is a development from the HULC exoskeleton, which stands for Human Universal Load Carrier. The Fortis is intended specifically for industrial use in shipyards, It is a device that allows the user more easily handle and manipulate heavy tools using different equipment. For this is unpowered, but its ability to transfer load to the ground may reduce fatigue and improve safety. All right, the next one, it's called X1. The X1 exoskeleton, which is in figure 1 that you can see, was built as a joint effort between NASA and the Institute for Human and Machine Cognition in Pensacola, Florida. It was intended as a potential means for training astronauts in space to prevent muscle fatigue and bone thinning. This device can be configured in a force control mode, allowing both eccentric and concentric exercises. And the last one I mentioned here, it's called HAL, H-I-L, which stands for Hybrid Assisted Limb Exoskeleton. The technology is used by patients with incomplete spinal cord injuries, stroke, and other deficits that impair walking functions. HAL has both unilateral and bilateral versions that activate the knee and hip joints. It is the only lower limb exoskeleton on the market today that utilizes remaining surface electromyography, EMG, signal information from its user. All right, that one we can see. Let me see if I can make it a little bit bigger. And figure 3, which is this one on the bottom, the one I'm picking right now, it's a number of exoskeletons being developed. On the left, we can see that Cyberdrine developed a hybrid hull, which is the one I just mentioned, which is to aid individuals with disabilities. The other one in the middle is the exoskeleton, which is used primarily for rehabilitation purposes. And the indigo exoskeleton in the right is the, let me see if I can just open this. There you go, to make it bigger. All right. It's from parking happening and is intended as an assistant technology exoskeleton to aid person with spinal cord injuries. Also, the ones above those are in the left is the Fortis exoskeleton, and the middle is the X1 exoskeleton, and in the right is the WIS Institute soft exoskeletons, which I think it's one that's starting from Bleaks. All right. All right, let's talk now about methods. Let me see, give me one moment. All right. The actuators on the exoskeletons are almost all the exoskeletons use electric motors. Give me 1 second. Just this is lagging. How do I? There you go. No. Stop video. Push. Stop recording. Stop sharing. All right. Sorry about that. I would just had to check something. Let's continue sharing my screen. Let me see here. Share. Let me just open this up. All right. As I was saying, the actuators, almost all the exoskeletons use electric motors inside the actuators, and DC motors and series electric actuators are the most common ones. On the left, we can see a design of an exoskeleton. And number 1 is a bone frame, which reflects the exotendon, which is mentioned later, knee pulley, and loose leaf spring. Also, sensors are part of the exoskeletons as well. Many lower limb exoskeletons use a position controller, and there's also the EMG sensors, which are, as I mentioned before, electromyography sensors, which is connected by the user to the user's, I think it's under skin, or the user can send their responses, what they want the exoskeleton to do. Usually the exoskeletons are controlled by a position by a controller, not through, let's say, the human mind. So these sensors can read what the user actually wants from its thoughts or its what do you call it? It's the waves, the electrical waves they perceive, and then they can activate as the user may want. Also, another part of the exoskeletons are the energy they use. Almost all exoskeletons use batteries to generate energy, and the strings and clutches are also used as the X, as in the XPED too, which they use an exotendon, which is right here to produce and store energy. Also, another one is another part of the exoskeletons is the control. One is force based, and the other one is position based. And the materials used in exoskeletons are mostly metal, and the metals used are usually titanium, aluminum, steel, carbon fiber, and there's also soft exoskeletons which are made out of carbon fiber and other different materials to make it more, to reduce the weight and make it more efficient. But they're still on the review. All right. These are some of the results that you can obtain from exoskeletons on the state of the art. The calibration and the setup times are still an issue. It takes a while to set up the exoskeletons in a user. The comfort and interface are also an issue for the user, which is most of, as I mentioned before, one of the metrics on developing exoskeletons is that users are not comfortable when using exoskeletons because either they're too bulky or they're too heavy, and that makes some people wary about using exoskeletons or not, and prosthesis in general. Also, another one is feed-forward neural commands, which I mentioned before, the EMG, the electromyograph electrodes, which are surface and intramuscular. Those are the ones I was mentioned that I think it perceives the current, the electric current that sends from the body to perform a certain action. Also, there's the IMES, which I believe is also underneath the skin, and epidermal electronics, which is above the skin. And these are an issue because, with sweat or sometimes the movement of the sensor, it's not steady. So it's always have to be checking to see if the position is well or not, and if the exoskeleton is receiving the direction of what the user wanted to do or not. And also another issue is the state of the machines, employed to specify different states of the controller, the neural information, and there are hybrid controllers as well. And as a conclusion, the components that need the most work relate to the frame, which is for comfort and energy transmission, as I mentioned before, and the actuators. Soft tissue interface between the device and the user's body is not particularly comfortable. Exoskeletons might not have enough degrees of freedom. Novel actuator design to not resemble current standard for autonomous robotic electrical motors might be a good way of implementing and improving the exoskeletons. And another one, improving the performance of single joint exoskeletons through better controllers and actuators will then presumably lead to further development and whole limb exoskeletons. All right, and that is for this presentation. Let me just stop sharing my screen, pause share, stop sharing, there you go. All right, this was my presentation for the week of June 20, starting in June 22.